Kia ora and welcome to workshop 4 for 161324 data mining. So in this workshop we're going to start on prediction. So the goal is to predict a measurement variable or a numeric measure using other data. And we're going to start with a model that you should be familiar with, which is the linear model or linear regression. And we're going to be looking at straightforward multivariate linear regression for this. And it's really the best candidate model to start with because you probably already understand it and know about it, and it's very straightforward. It's computationally simple, so the mathematics behind it is very simple, and it can be used for multiple things. So for example, a lot of the time they use linear regression is to explain something, i.e. to relate a outcome variable to one or more predictors, in the sense of trying to infer what relationships exist. In the data mining sense, or at least how we're planning to use it, we're not so interested in explaining what is happening necessarily. So our process, so our outcome isn't really inference. Instead, our outcome is basically just predictive performance. So we want a model that predicts the outcome variable as best as possible, and we don't care quite so much in explaining how that happens. Now, of course, the linear model we'll be able to easily infer that information, the explanatory side of things. But some of the other models that we look at later are going to be a little bit more like a black box. So we're going to use some data today, which again is quite old. It comes from data from a Sun SPARC station, which is an old sort of mainframe type computer running in a university department. And we've got a whole bunch of measure variables. So all of these, I think, are numeric, which are basically to do with the things that the computer is doing over time. And we're particularly interested in the target variable user, which is the percentage of time that the computing processor units, the CPU, the thing that does the work, is running in user mode, which basically refers to doing work for the user, as opposed to doing work for the system, for example. And so our goal is to use the first set of variables in order to predict the user one. Okay, so we've got 21 measure variables available and one outcome. So we're going to start by loading some packages and the data. Now you may find that you need to install a few of these because we haven't discussed them before, such as RSample, which is used for subsampling data, and Yardstick, which is used for evaluating model performance. So you may have a wee yellow band up here when you loaded the lab up, suggesting that you should install some packages. Go away and install those as needed. So we've read this in. You possibly may need Broom as well. Right, so we've read the data in. We get to take a look at it. So you can see that we have 800 entries, 22 columns, and we can see that they're all numeric. So the first thing I notice is that they're all on very different scales. So some are in the thousands, some are only in the tens and hundreds, some are in the hundreds of thousands. So that's something to make note of. Here's the outcome variable. And it generally looks pretty complete. Obviously we could do a skim and perhaps find out that. So we'll start using that. So you can see that we have 22 variables, of which all of them are numeric, or at least the computer thinks they're numeric. And as we go down, we can see that we have no missing variables on the first few. The distributions are potentially quite skewed, so you can see here that the maximum value of this column is 2.4 million, and the minimum is 400,000, and the median's 100,000. So that's skewed to the right. A lot of these seem to be skewed to the right. No missing values on these ones. Right, no missing values at all, so that's good. We don't have to worry about that. Of course, we could visualize it if we wanted to with the vismiss function from Narnia. Okay, so you may need to type Narnia first. I think I've already got that package loaded. So you can see here that it's 100% present. That's good. So now what we want to do is kind of get a feel for how the variables that we have to act as predictors, which are the first 21 variables, are associated with the last variable, the user variable. And because they're all numeric, we could use scatter plots, and we could start just by sort of doing one by one, right? So if we just look at the very first one, which is the lread variable, we get the scatter plot here, and you can see that perhaps there's something going on, and that it's a decreasing trend between lread. So as lread increases, the user variable tends to decrease, but this is a very skew variable, and so potentially we might want to put this on a different scale to see what's going on, but we can see generally there might be something going on. There's a lot of scatter around the trend. We could try out a different scale, e.g. putting lread on the log scale. So we could do that just by adding scale x log 10. Yeah, so that looks somewhat better. So now you can see that lread is on a log scale. Notice that the transform introduced infinite values in a continuous x-axis, and the reason is that lread can take values of 0, and the log of 0 is minus infinity, and that's what's stuffing it up. So a common sort of trick here is because lread typically takes large values, right? If we look at the plot for lread again, while there are some zeros, most of them are in the tens or hundreds. Then adding 1 to it doesn't really make much difference in terms of the distribution. All it's going to do is shift it a little bit to the right. And so if we add 1 and then take the log, we get rid of the problem of taking the log of 0. Okay, and so now we get no error, and these ones back here are the ones that have lread of 0 because we've now changed it to 1. Okay, we still see the same sort of trend. So there's a general decreasing trend. With log lread. So might want to consider taking the log transform of some of these variables for our modeling. Remembering that we're fitting a linear model, i.e. straight lines. Excuse me. Right. So we could also do this with the second variable, so we could do the same thing, right? With our right, I think, is the second one. Okay, and we get the same type of thing, right? And we could see that maybe we want to log transform that one as well, right? So we could do the same thing. And so on. Okay. But we've got 21 variables to do, and that's going to take a long time. So a trick to do them all at once is to use faceting, to use small multiple plots. But you remember, in order to do faceting, we need a variable in our data for the facet. And we need our data in long format. Now, this data is actually tidy already in that we have a single observation per row and a single column per variable. Right, so it's actually tidy, but what we're going to want to do is we're going to want to make it untidy in order to produce a nice plot all at once. So it's sort of a tidy plot, if you like. So what we're going to do is this trick here. So the first thing we're going to do is we're going to add an ID column. Now the purpose of the ID column is just so that we can undo this process later, right? So first of all we use the function row ID to column, which adds an identifier. So it's just 1 through 800. And the reason for doing this is that once we push it longer, we make this data longer, then we're going to need to know which of the multiple columns that we create for each observation are the same observation. So which one is observation 1 and which one's observation 2 and so on, so that we can then back transform if we need to. So that's the purpose of adding a row ID. And then given the row ID, we're going to pivot longer, and so what we're going to do is we're going to take our columns from everything except the outcome column, the user column, because that's the one that we want to always be on the y-axis in our scatter plots. And we don't want the ID column because that's kind of useless to us. That's just the unique identifier. We don't want to pivot that because we need that to stay as it is, so that we can actually associate these extra rows that we create with the same observation. The names and the values are just going to be name and value. So let's run that and see what happens. We've got to put a pipe in there. Okay, so what you can see has happened is that now we have our ID and user column, right? Those have now been replicated. So I've got 21 observations for ID 1, right? It finishes there. And for each one, I've got the corresponding variable and its value. So this is very much untidy in that I've got 21 rows per observation, and I've got the name of the variables in a column instead of having a separate column per variable. But now we can plot this because we just got two columns, user and value. So user we can put on our y-axis, the value we can add on our x-axis, and then we can facet by the name variable. And it'll give us our scatter plots all at once. But before we do that, let's check that we can get back to the original data. You know, have we, can we actually get back and make sure that we haven't changed things? And so one way to do that is to pivot back wider. So let's create a new one. So comp wide is going to be, well, let's start with our comp long, and we're going to pivot wider. The names from are going to be, we're going to take our names from the name column, and our values are going to come from the value column. There we go. So you can see it's back to the same shape it was before, 800 by 23. But now you'll notice that the columns aren't in the same order, right? So we've got our ID column and our user column. Well, for a start, ID wasn't in the original comp data. We added it in the process of creating comp long. So that's a new column we didn't have before. Our user column used to be the last one, but now it's the first. And there's no guarantee that these next columns are in the same order. I think they happen to be in this case, but there's nothing to guarantee that. So for example, in comp long, I could have rearranged things, right? And similarly, there's no expectation that the rows will be in the same order necessarily. In this case, they happen to be, or at least they look as though they are. But again, I could have rearranged the data any way I liked in long format before I'd done this pivoting. And in fact, the process of pivoting doesn't need to guarantee that things stay in order. Okay. Computationally, it might actually be better that things not stay in order, because in order to pivot wider, what you've got to do is you've got to find all of the, you've got to create all those new columns and then collapse them down, collapse the rows down into a single row, and doing that requires you to essentially group by the columns that you haven't pivoted. So in this case, the ID and the user, so that you get a unique entry first. And whenever you need to group by something, typically sorting the data is the most efficient way of doing it. Now, this may have actually been done, and it just so happens that ID is already sorted, and so everything comes out nicely. But there's no guarantee of this. So the point is that comp-wide, in theory, should be the same as the original data comp. Obviously, we've got the extra column ID, but other than that, it should be the same. We'd like a way to verify that, but we can't verify it just by putting them side by side or comparing them with equality, for example, because the order of things aren't the same or aren't necessarily the same. Okay, so let's just write a note about that. Right, so potentially reordering things might be quite tricky. And so there's tools for this, and one of the best ways to do it is using an anti-join. So an anti-join is an example of what's called a filtering join. So the two types of joins in dplyr are mutating joins, which are your left join, right join, inner join, full join, cross join, and so on, which create typically take a data set and add columns, just like mutate normally does. And then the second type are filtering joins, which don't add new columns to the data set on the left, and instead use the rows in the data set on the right to filter your data. So essentially, you only return rows for which there is something found on the right-hand side. So the idea is we could take our comp data and we could anti-join it with our comp-wide data. Right, and you can see I get 0 rows. There are no rows in comp that are also that means there are that are not in comp-wide. Everything in comp is in comp-wide. So that guarantees coverage in one direction. You can see that the join has been matched on all our variables, except ID. So ID is not in here because comp doesn't have it, of course. And then we could do the anti-join the other way around. So this guarantees that everything in comp is in comp-wide, but potentially we could have things in comp-wide that aren't in comp. So doing the anti-join in both directions is useful. Okay, you can again see that it's joined by all those variables and it's returned no rows. This means everything in comp-wide is in comp. So they must be the same. Right. Everything in comp-wide is in comp, and everything in comp is in comp-wide, so they are equivalent. So that's just a handy way of checking that when you mess with your data by making it longer or wider or whatnot, you can always go the other way just to check that you haven't dropped rows or whatever. It's most useful after you've processed things. So in this case here, all we did is we went longer then wider. Right, that's just basically going to reverse the same process, so it's no surprise that perhaps things have no problem. Typically, once you go longer, you might do some processing on that data, and then eventually you'll want to check whether you haven't accidentally dropped a row or something. So now that we have that long data, the whole purpose of that, of course, was so that we could do a plot. So let's do the plot. So what we're going to do is we're going to take our comp long data and we're going to throw it into ggplot, and we're going to do a scatter plot of where x is going to be the value and y is going to be the user variable, right? So if you remember what comp long looks like, right, we have our user, our outcome variable that we're trying to predict, and what we're wanting to do is find the relationship between that and each of these variables, the values for which are in the value column. So we're going to put the value on the x-axis, and then we're going to facet by the name variable. And that will give us our scatter plots all at once. Now, what you'll notice is that many of these scatter plots look kind of useless. And the reason for that is that these are on very different scales. Okay, so if we look at the help for facet wrap, we find that there's an argument scales, which defaults to fixed, but could be free x for a free scale in one direction. Obviously the y-axis is going to stay the same. Okay, and so there you go there. Okay, and so what we can see here is that there does seem to be fairly linear relationships with a bunch of these variables. So with exec, with fork, with pflt, with vflt, with swrite, with sread, with scall. Many of these are sort of decreasing relationships. Free swap is unclear. Free mem is unclear. Maybe it's going up. So the more free memory you have, the faster, the more time you can give in user mode. That kind of makes sense, I think. Some of these obviously have some big outliers, but that's okay. So this is potentially reasonable for a linear model. Have a fairly linear relationship with user. So a linear model might be expected to do reasonably well. There are some outliers and some might need some transformation, e.g. our read and our write, which we can play with later. Okay, so now we want to build a model, build a linear model relating these variables to the outcome variable user and seeing how well we do with prediction. But before we do that, we're going to need a way to measure our predictive performance. And you remember from lecture 4 that we don't want to fit our model on all 800 rows and then do our evaluation of predictive performance on those same rows, as if we did that, a model that overfits to those 800 rows is going to come out as the best, right? Because we're measuring performance on the data that it's used to train the model. So we're going to have home ground advantage, and we're going to get models that overfit on the training data. And then when a new data set comes along that we haven't seen before, it's probably going to perform poorly because it's sort of overfit itself onto the data that it's seen. So instead what we're going to do is we're going to deliberately create two sets of data that are going to act independently. So we're going to take our 800 observations and split it into a training set and a testing set. We'll then build the model purely on the training set, and then we'll evaluate its performance on the test set, which it won't have seen before. Okay, therefore, models that overfit on the training data, on those 600 training rows, are likely to do worse on the 200 rows that they haven't seen before, whereas models that perhaps don't overfit and are perhaps more general will then do better on the test data. So the test data, those 200 rows that that the model won't have seen before are sort of an independent set for evaluating performance. And we're going to do this with the R-sample package. So the R-sample package is essentially a package in the Tidy Models framework for splitting data or resampling data. So R-sample can be sort of thought of as resampling. You can do things like cross-validation and so on. And we're going to use the initial split command, which takes a data set and the proportion. The proportion is obviously a number between 0 and 1 that describes how much goes into the first side of the split. Okay, so all this does is create the split. We're going to set the seed, which sets the initial value of the random number generator so that things are reproducible, i.e. you will get the same split that I do. That's going to be important later. And each time I run this, I'm going to get the exact same split. So all that this initial split function does is define the split. So the variable split just tells us that in my training set I've got 600 observations, in my testing set I've got 200, and in the total I've got 800. Now the function tidy then gives us a data frame with that information. So let's run that. The unique ID, unique index, if it's set to false, it will return the row number in the original data set. If it's set to true, which is the default, it will generate one. Right, so that's the difference between those. In this case, because it's got a unique identifier, it can use it anyway. Right, so you can see here that each row in this tidy data set is telling you which row it's picked from the original data. So the first two rows are in the analysis set. The third row is not, so that must be in the assessment set or the testing set. And similarly, rows 5 through 7 are in the test set. Okay, so if we go far enough down in here, we'll see where it transitions. It'll be about page 60, won't it? Okay, so there's the last row in the analysis set, and there's the first row in the assessment set. So you can see that row 3, 5, 6, and 7 are all in the assessment set or the testing set. So all we've done is we randomly allocated 600 of the rows to the training set and 200 of the rows to the testing set, and it's done it in a random fashion. Now, of course, you don't have to do it this way. You could do it some other way. So, for example, you could you've got 800 rows. You could just uniform random sample from the numbers 1 through 800 using, say, the sample function. That'll give you the indices that you need to sample for the assessment for the training set. And then you could use something like an anti-join to get the test set. The initial split function just sort of automates that process. Okay, so let's explore this a little bit. Find the first row allocated to the assessment set, right? So we could just use our tidy information there. Right, and then we could just filter on the data variable. So we can see that it's row 3. Okay. To the testing. We could check we have 600 analysis and 200 assessment rows just by doing a count. So again, we could take that tidy data and we could just count. And sure enough, we do. Okay. So now that we have our split defined, we can now run the training and testing functions on split, and that will pull out the 2 data frames that we need. Okay, so now we could have a look at comp train. there it is there, 600 rows, and comp test, there it is there, 200 rows. And again, we could check that this covers the entire data set, so we could bind those together. All right, that'll give us our 800 rows. Now, of course, they won't be in the same order because these rows were picked at random, but they should, if we anti-join them to comp, we should get no rows returned, right? So we've got complete coverage. There's nothing in comp train and comp test that aren't in comp, and similarly the other way around. If we anti-join the other way, there's no rows, right? So comp test and comp train completely cover our original data. We can check with some anti-joins. Okay. So now we're going to start fitting our linear model. So we're going to use just our training data, and we're going to fit a model, a full model, so a model for a user in terms of all of the data. So you remember the LM command takes a formula syntax. Okay, the left-hand side of the little tilde. Tilde means in terms of. Tilde is in the top left of your keyboard if you haven't used it much. So this is modeling the outcome, the target variable user in terms of everything. So the dot means everything else in the data frame. And we're going to use comp train for that. And so we've created our model 1, and now we can look at model 1 using the summary information. So you can see that we've got our estimated coefficients. So those are our betas in our linear model equation. 1 per 1, we've got the standard error associated with those, and then we've got the p-value, which is assessing essentially the magnitude of the estimate compared with the standard error. The t-value is just estimate divided by standard error. It's just the how many standard errors the estimate is away from 0. And you can see that a lot of the variables here are highly important. More stars, more better. Some of them aren't. So these ones here, for example, don't seem to be important. Nor does this one. That doesn't mean that they're not important variables. It just means that once you've got the others in the model, this one is no longer perhaps necessary. So there may be some tuning to be done on this model yet. We may be using more variables than we need to, and therefore estimating more things than we need to, which is going to contribute to the variance of the estimate of our model. You can see that we explain a lot of the data. 93% of the variation in user is explained with this model, so we're doing reasonably well. Now, this summary output is sort of untidy. It contains multiple things in tabular form. It's hard to extract numbers from that summary information. So the glance function is a function from the Broom library, and it's used to just pull out the information from those bottom 3 rows into a nice data frame form that we can then use. So for example, we have our R squared pulled out from here, our adjusted R squared pulled out from there, our F statistic is there, p-value is there, and degrees of freedom and so on is all there, plus some other information like log likelihood, AIC, BIC, deviance, a bunch of other stuff. Okay. So let's answer some questions here. How many predictors are included in Model 1? There are 21 predictors included in Model 1. Everything other than user. Right, we could just do that just by counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. The other way we could get that is we could just look at the degrees of freedom. Right, that's 21. The DF column will also tell us this. Well, it tells us how many numeric equivalent variables in the model. E.g., if we had a categorical variable with 4 levels, it would need 3 indicators in the model would contribute. Okay, so which predictors don't seem to be providing much information? So we could have a look at our summary information here. So we can see, for example, that the L-read has a higher p-value, so does fork, so does these pgout ones. So let's write a bit about that. Okay. So a tidier view, just like glance, pulls out the sort of as a tidy way of pulling out the information from the bottom of the summary table. The tidy function is a tidy way of pulling out the information from for the coefficients. And the advantage of this is now, you know, it's tidy, right? It's now in a data frame. So we could, for example, we could filter anything with a p-value is greater than, say, 0.2 or something. And so we know that these things here are the variables that the model is saying are not strongly important, right? Because they've got a high p-value. Right, so we don't have to worry too much about reading things from a table. We can use the computer to pull out the things that are important. Okay. So now we're going to assess predictive performance. So to do this, what we're going to do is we're going to take our model and we're going to feed it the data from our test set. That's the data that it hasn't, those 200 rows that it hasn't seen before. We're basically going to plug those 200 rows into the equation that it's defined, and we're then going to find the fitted value and find the estimated user variable, and then we're going to use the real user variable, which of course we have in our artificial test set or validation set that we've created here. We're going to use that to see how well we did. So we're going to use the augment function. So the augment function takes a model and some new data and does the prediction and creates a bunch of extra columns for us. So let's run this and see what happens. Right, so note that I'm using select here to reorder things so that the user variable and our fitted variable come out first, and then all our predictors plus other information. So we've also got a residual column. So that's already computed, if you like, the difference between the true value user and the fitted value dot fitted. So you can see that the difference between these two numbers is about 0.55, which is that number there. Okay, so you can see that we're doing reasonably well. If you just sort of scan down here, the you know, this is pretty close. When the numbers are bigger, the numbers are bigger, and when the numbers are smaller, the numbers are smaller. That seems to make sense. We could summarize the now that we have this prediction, then we could compute the mean square error. So the mean square error is going to be the difference between user and fitted squared. Then we take the mean, right? So that's the formula for mean square error. So you can see the mean square error is about 6. An alternative way to do this is to use a function another person has written. Obviously, this is a thing that we'll be doing over and over, and we don't want to have to, you know, type this formula out by hand all the time. particularly because we might accidentally mess up at some point and use the wrong column name or forget the square or whatever. So this is a thing that we're going to be doing all the time, and things that are done all the time generally have packages for them. So we're going to be using the yardstick package, which is for measuring things. Obviously, the name yardstick is refers to that, of course. And it contains a bunch of functions for measuring predictive performance out of models. So it's part of the Tidy Models framework. And one of the things that it provides is the root mean square error. The reason it provides the root mean square error instead of the mean square error is the root mean square error is on the same scale as the outcome variable is. So it's on the same scale as the user variable, whereas the mean square error is not, right? Just like the variance is on a squared scale, and the standard deviation, which is the square root of the variance, is back on the same scale as the actual measure. The root mean square error is on the same scale as the outcome variable. So it's on the same scale as user is. So RMSE takes two columns, the truth, which is going to come from the user column, and the estimate, which is going to come from our fitted column. And it basically does truth minus estimate squared, computes the mean, then takes the square root. Okay. So that's one model that we could have. However, we could fit a bunch of other models, right? We could do some model selection here. And so we're going to compute some other models. So we're going to do a couple of other ones, a model with all predictors except some, a model with just a few, and then a model done with stepwise regression. So our second model is going to be, we want all predictors minus the ones specified. So minus L right, minus ATCH, minus S right, minus pitch out, data equals comp train. We could then look at glance. So we could see that that has an R squared of about 93%. So this model's doing pretty much as well as the original one was doing. We could also do predictions. So we could take model 2 and augment it with our our testing data. And then we could do our fitting. So truth is user, estimate is not fitted. Okay, so we can see that this does quite a bit better. Its root mean square error is 1.93. Okay, and then we could do some other models. So model 3 is going to be user only in terms of these variables here. So we want R, U, N, Q, S, Z, free swap, free mem, PFLT, L read. Right, and then we're going to need, we could again take a glance at that model. You could look at the coefficients as well if you want to. So this one isn't doing as well, R squared, so we'd expect predictive performance will be a bit lower. Let's see. Let's do some predictions from this model. And then use yardstick to compute the RMSE. So okay, so 2.4, so we're worse, but actually still better, I think, than Model 1, interestingly enough. So we're much better in Model 2, but we are better in model 3. Notice that that what I'm doing here, the processing side of it, is the same in each case. So it's actually highly inefficient to do what I'm doing. It'd be better to somehow automate the fitting of all the models and then automate the process that comes out of it. And we'll learn to do that later on when we look at the titled models framework. So let's now do some stepwise regression. So we're going to start with model 1. We might call this model step maybe. We'll just call it model 4. So we're going to run a step on model 1. You can see it spits out a bunch of things. So the first thing it's going to remove is PPG out. Then it's going to remove PG out. So it has the best IRC. Then it's going to remove fork. Then it's going to remove PG in. Then it's going to remove rchar. Then it's going to remove lread. And then it's done. Right, so the no changes is the best. And so that's the final model here. All right, so we could just tidy model 4, all right, to see that. So there's the. Now notice it's still used some that have a high p-value. So you can see here we've got a p-value of 0.15. Here's another p-value of 0.15. So it's not as if it's eliminating everything with high p-values, because some of them have been left in. Because it's using a different criteria, it's using that AIC criteria. So let's do prediction from this. So again, I could just copy and paste these lines, couldn't I? Change all the 3s to a 4, and we'll be done. Okay, and we get 2.22. So the best model in this case happens to be this one here, model 2. And the stepwise one doesn't perform as well. So model 2 performs the best, as it has the lowest RMEC. On the test data. Now, one thing we want to do now is look at this number and just see whether it makes sense, right? So regardless of what it is, we can use it to choose which model is best. But it is actually something that we can compare to, for example, the standard deviation of the user variable to begin with, right? So this is, if you like, a measure of, it's a similar measure to standard deviation, really. So it's essentially the length of the uncertainty that we have after at our prediction point. So we can compare that to the amount of variation that was in the data to begin with, because presumably we've explained a whole heap, right? So these models had R-squareds of something like 93%. So presumably we should have explained 93% of the variation, and so we've got just a small amount left. But what we actually find is that if we just take our training data and compute the standard deviation of the outcome, then the standard deviation of the outcome is 7. So what we've done is we've fit a model and we've reduced essentially so, one thing you could do, kind of a very silly model would be to say, well, all we're going to do is we're going to say, regardless of what our observation is, our model is just going to give you a mean of the user variable. So we could just compute the mean on the training data and just use that for everything that we see. Then we would expect our root mean square error to just be the standard deviation of 7. Right? So that's not going to be a very good model. It's going to be a very rubbish model because it uses no information other than the mean on the training data. But the models that we have are obviously better than that, but they're not dramatically better, right? We're reducing it by, about a factor of about 3 or so. So all we've done is reduced our predictive accuracy from a very silly model down by a factor of 3. So that's not particularly impressive. And so what might be going on here? So we're going to have a look at it in a little bit of detail. And what we're going to do is we're going to take our predictions from model 1 and we're going to plot them. So this is a sort of a simple check that you should do to make sure that things aren't very strange. Because what we'll see is that we have strangeness. So you see this observation out here that is very far away from the truth. So that we've got the truth on the x-axis here and we've got our estimate on the y-axis. And you can see that our estimated user variable for this particular data point in our test data is miles away from the actual value. So the actual value was about 74 and we've said it should be closer to 95. Now what we're doing, of course, when we're computing the root mean square error is we're computing the distance away from the truth, which is in this case for this observation is very large. We're then squaring it, which makes it even bigger, right? So this would, the magnitude here is what, about 20. So we're squaring it, that'll be 400. And then we're adding them all up. And of course, these ones will all have magnitude, maybe, the error might be 3 or 4 or something. So when we square them, we only get 15 or 16. So each of these gets like 15 or 16. This one gets 400. So it's massively affecting that root mean square error. Okay? And so the reason we're getting such high root mean square error is because we have an outlying observation, or one for which our prediction is very bad. All of the others, the prediction is very good, but for this particular point, we're getting a very bad prediction, and that's influencing the root mean square error. So, being strongly affected by this one extreme prediction, where we're out by about, whereas all the other observations are plus or minus 3 units. Okay. So an alternate to using the root mean square error is we could use a different measure that doesn't have the squaring process. So for example, we could use the mean absolute error, which is basically this computation here. Okay, where instead of taking the difference between user and fitted squared, we just take the absolute value. Okay, so we can do it two ways. We can do it manually. We find it's 1.6. Or we could do it with the yardstick package, the MAE function. So we could compute the mean absolute error for each of these models, and now we could compare them with this one. So let's do that. So we could take model 2. Well, let's just do all of them. I've been a bit slack here, haven't I? I should be saying truth equals and estimate equals. Right, and then I'm just going to copy and paste that. So there they all are. So we've got 1.6, 1.48, 2.02, 1.56. So again, model 2 is better. Okay. I guess I could show you how you would do this all at once. So one thing we could do here is we could go, well, we could basically bind our models together. So we could bind rows So we could create a list. And then we could, right, so what this does is it puts each of these predictions next to each, above each other. So we've pasted them together row-wise. So we'll have a block of 200 with model 1, which are the outputs from model 1. We'll have a block of 200, which are the outputs from model 2, a block of 200, which are the outputs from model 3, and a block of outputs from model 4. And then we could group by model. And then run the MAE. Okay. And we get it in a nice little summarized table where we've got model 1, model 2, model 3, model 4, and our estimate. Okay, so that's how we can do it all at once. Now, you can see that this contains almost the same amount of code that this did, but the advantage, but you know, most of the code is actually constructing the list. And one way that we'll end up doing things, or one way we could end up doing things, is that model 1 pred, model 2 pred, model 3 pred, model 4 pred, etc. were all constructed in the same way. So we could have started with a list of models. Right? So we could have started with model 1, model 2, model 3, model 4, and we could put those into a list, and then we could process them as a list to get a single prediction, which would be all of this. And then we'd just group by model and compute the MAE at the end. Okay, so there's advantages to this past the fact that we only have to run the MAE function once. Nothing really wrong with this. It's just you can imagine if you've got 70 models or something, this methodology is going to be better. And the tidy models framework that we'll learn about later is it contains functionality to basically take care of that processing side of things. Now at the end you may want to try tuning the model. So for example, you know, some of those variables might be better with a log transform. You might want to play around with that. We also might want to find the row that's bad. Okay, so what is this one here? So that's easily enough to find. We can see it on the plot. So we can see it's the only one where the fitted value is bigger than 90 and the user value is smaller than 80. Right, so if I sort of chop out based on these lines here, so the problem row is the one that has user that has our fitted value greater than 90 and user less than 80. Right, so we could use a filter. It's dot fitted, isn't it? There we go. Single row. So problem row. Now we don't know why it's a problem. So one way we could see why it's a problem is we could add this row to our training data, and then we could chart it by looking at the relationship between the user variable and all of the other variables. And seeing if we can pick out the problem. Because probably what's happening is that we know, for example, that the user variable itself for that observation is not unusual, right? It's right bang in the middle of the data, a value of 74. It's just the fitted value that's unusual, which suggests that the reason the fitted value is unusual is because some of the covariates are unusual. So it perhaps has an outlier for one or more of the variables that have been used in the model, so that when we bung it into the linear model equation, it's giving us a very different result to the true answer. So it must look different to the training data that we've seen before. So that's why adding it to the training data might be a useful thing to do. So what we're going to do is we're going to take our training data. Let me think. Probably what we're going to do is we're going to create a list of our training data and our problem data. And we're going to bind them together where the ID field is maybe problem or something. Okay, so here you can see I've got 601 observations. The problem column tells me which is which. And eventually, if I have a look at the last one, it's called problem. Okay, and then I've got all of my predictor columns. Oh, I've also got these two, which I don't really want, do I? Because I only have that for the final observation and not the other rows. So let's maybe drop those. There we go. Now we've got 23 columns. So we've got the 22 columns. 21 predictors plus the outcome plus the problem column. So now what I want to do is I want to plot the relationship between each of these predictive variables and the outcome, just like we did earlier with the long form data. So we're going to pivot longer. We don't want to pivot the problem column or the user column. Maybe I'll call it variable. Okay, so there we go there. So there's our problem column, our user column, there's the variable, and there's the value of the predictor. And then I can throw that into ggplot and do some scatter plots of our predictor X value versus our Y value of user, faceted by our variable, just like we did earlier on with the conf long. It's geonPoint, not geonPoints. There we go. Oh, we're going to have to scale out, change our scale with X. So that's our training data plus our odd one. And now we're going to color by the problem column. So we can see that the red dot is the one that's the problem. That's the one that's in the test data, that's not in the training data. And the blue ones are all our training data. And so you can see that in many of them, it's not strongly unusual. But in OWLRead, it is strongly unusual. And of course, Model 1 used OWLRead, didn't it? Okay, if we have a look at Model 1, so let's just write a little bit about that. So we find the observation, tack it on to the training data, and explore the relationships between each predictor and the outcome, coloring by whether it is the problem row or not. So the idea here is that the problem row had a typical user variable, user outcome target, but an atypical prediction. So it is likely to be atypical in one or more predictors compared to the rest of the data the model has been trained on. In this case, it has an extreme LRead value. What is the model doing with LRead? So we could just have a look at the, we could just run the summary command, I guess, or we could use tidy. So if we have a look at the summary, we can see that LRead has a positive coefficient. Okay, and so when the value for LRead is a lot larger, then the outcome is going to be higher. And that's what we've seen in this model. Okay. It has a positive effect, i.e. larger LRead gives larger predicted user. This is what is happening. Okay, so for example, we perhaps wouldn't see the same issue in a model that didn't include LRead. Okay, and that's part of the reason that some of these other models do much better, because if you have a look at these other models, Model 2 had LRead, so that should still be affected. Model 3 didn't. Oh no, Model 3 has LRead, so that should be affected. What about Model 4? Let's have a look at what Model 4 had. Yeah, Model 4 didn't have LRead, and so that won't be affected in the same way, okay, as the other models. Okay, so that's what's going on in that case. So it's one thing to just to be careful of is that you want your test set and your training set to be similar, right? So that the model that you build on the training set is going to perform well on the test set. You don't want them to be the same, of course, but you want them to come from the same universe, if you like, the same population. And in this case, we just happen to have one extreme value in our test set. So it's just something to look for, is that, if we randomly split it, the data into test and training in a different way, say, we use a different random seed or whatever, then we might not have got this, right? That observation that's extreme might have ended up in the training set, so the model would have seen it before and been able to account for that type of thing. Okay, so just be careful. So a simple sort of sanity check is plotting your predictions versus the real value on your validation set, just to make sure that you don't have any real strange observations that are contributing to your mean square error, and is thus affecting your decision that you're making on what the best model is.